So end of part 2 from yesterday's lecture was here. So we discussed the space-time interval, and I claimed that it's an invariant. I showed that it's invariant. And this is kind of a big deal because I showed that kind of all of the relativistic effects are buried in this invariance. And you can also use it to solve problems. But notice, if it's an invariant, the sign of this also has to be invariant, right? So if this is like number minus 25, then it's minus 25 in all frames, including the fact that it's a minus 25. So the sign of the space-time interval is also invariant. And therefore, it's a useful thing to do to classify space-time intervals depending on their sign. So again, I have event 1 and event 2. They're separated by space and by time. I literally just compute this quantity right here. And I see, okay, it could be a positive number, it could be a negative. It's positive if it's separated more by space than by time. And it's negative if it's separated more by time than by space. Okay, so if it's positive, if the events are somehow too far given the time, and it's negative if the events are close enough given the time. So it's something like that. So okay, so here are the 3 types of intervals one can encounter. If delta S squared is negative, yes, delta S squared can be negative. It's called a time-like interval. Well, it's called time-like interval because the time part is more dominant than the space part. You can also see that, notice, if it really is, if in some frame 2 events really are separated only by time, i.e. they take place at the same location, event 1, event 2, delta x is 0, then in this special case, delta s squared is clearly minus c delta t squared, so it's clearly negative, right? But let's say you have 2 events that, when you view it from some frame, they're separated both by space and by time, but it so happens to be that delta s squared is negative. Okay, they're separated more by time than by space. Well, then one can show that if that happens, if delta s squared is negative, there is a reference frame. There exists some co-moving frame in which those same 2 events take place at the same location. I will give you an example. Let's say you're in SLO, and let's say there's a concert in LA 9 hours from now. You hop on a train. I think Amtrak is just about right to reach LA in 9 hours. You hop on a train. When you leave SLO, you are at x prime equals 0 or x prime equals 5. You don't have to sit in the back of the train. And when you arrive to LA, as long as you're in the same seat when you arrive to LA, you're still at x prime equals 5. We discussed that yesterday, right? When in the beginning of the first lecture yesterday. In the coordinate system that's welded onto the train, in that coordinate system, leaving SLO and arriving to LA took place at the same location. So here we go. We have 2 events. You leaving SLO and you arriving to LA. From the perspective of your friend in SLO, the events took place at different times in different places. But because there was plenty of time given the separation, okay, plenty of time even for Amtrak, then you could find a reference frame, the train's reference frame, where those events took place at the same location. So this is actually straightforward stuff. So this was an example where the space-time interval between the 2 events was negative, and yes, you found the frame, namely Amtrak, from which perspective the 2 events take place at the same location. Okay, that's all it is. Now, what if delta s squared is positive? Well, that can happen, and it's called a space-like interval. Again, it's called space-like interval because it's more of a space than time. The delta x squared is bigger than c delta t squared. An example again is a pair of simultaneous events. Boom. They took place literally with delta t equals 0. So in this special case, where the two events are simultaneous, delta s squared is just delta x squared. Okay. But what if the two events are not simultaneous, but delta s squared for that pair of events is still positive? Okay, they're not simultaneous, but delta s squared is positive. Let's say event 1, event 2. They happen too close in time given the space, or too far in space given time. Then delta s squared will come out to be positive. And one can show that if delta s squared is positive, if it's a space-like interval, there exists a frame in which the two events are simultaneous. So this is a little bit harder to visualize than my train example. So if it's a space-like interval, you cannot find a frame in which the two events take place at the same location. You would have to go faster than light for that. Okay, you can't find a fast enough train. But you can actually find an event, you can find a frame in which the events are simultaneous. That one is a little bit harder to see, harder to visualize, but that can be shown. And these red things that I say you can show. So in lecture 3 from yesterday, I do show that geometrically, using the geometric aspect of this thing, the interval, which looks kind of like a Pythagorean theorem with a minus sign. So you can believe me that there's a geometry related to it. And in that part of the lecture, I do discuss that geometry. In any case, so yes, so you can have these types of intervals. And finally, if delta s squared is 0, well, that means that delta x squared equals c delta t squared. Oops. Right, so you see, if this is 0, then delta x squared must be equal to c delta t squared. This is called a light-like interval. A light-like interval. You have event 1 and event 2, and event 2 can be reached from event 1 only by a light signal. So if delta x over delta t equals c, then only light can reach, only light can jump from event 1 to event 2. Only light can make it, and it's called a light-like interval. Now, there's a lot of depth to this thing. This is just scratching the surface, but I told you what you need to know in order to do that homework problem, okay? I think I better stop it here, and I'm gonna start the new video with the new material, okay? I hope this one came out all right technologically, okay? See you soon.